Okay, hi everyone. Welcome back again to this second semester. And in this second semester, we are going also to be together in the two courses for those who are doing Bachelor of Technical Education in Mechanical Engineering, and for those who are doing Bachelor of Technical Education in Electronics and Electrical Engineering. This means for those who are doing BTM and BTE. Now, for those who are doing Electrical Engineering, this course is called MS 8121, and this is Advanced Mathematics. This is Advanced Mathematics. And for those who are doing Mechanical Engineering, it is called MS 8102 Engineering Mathematics 2. Engineering Mathematics 2. So these are two courses containing almost the same content, though in advanced mathematics there is a little content which will be added, but it will be the same, almost the same for those two courses. And good enough, the course has got the same weight of credit 5. And actually, in these two courses, which actually I will consider as one course for online distance learning, we are going to study mostly about the application of Fourier series in the engineering field, both in mechanical engineering and in electrical engineering. So in general part, we'll be dealing about, let me say it's about course aim. The course aim is, as I've already sent to you the course outline. We've seen the course areas and the course aim, but just for briefing you, the course aim is just to equip you students, to equip you with the knowledge of practical applications in practical applications of practical applications of Fourier series in the engineering field. So actually there are some areas which we are going to deal with. Actually, we'll deal with Fourier series themselves. We'll deal with Fourier integrals. We'll deal with Fourier transforms. Also, we'll deal with line integrals. Line integrals, and multiple integrals. So these are major areas which we'll go through in this course. And so we'll start with Fourier series. Let me go straight to Fourier series. So let's say this is our first session. In our first session, say this is session 1, we'll be discussing about Fourier series. So what are Fourier series? We say normally these series are very, very useful series. We say these are very, very useful series used to convert or to transform the discontinuous functions to continuous functions being represented by cosine and sine series. So these are Fourier series. We say these are useful series used in representing or converting discontinuous functions into continuous functions, but these are continuous functions being in the form of cosine and sine series. So these are Fourier series. Actually, when we say discontinuous functions, it means these are functions which, when we represent them, their graphs, they are splitting. They are not continuous. They are discontinuous. They are almost, we say, these discontinuous functions, we say they are like periodic functions. So we say these, so we say, these discontinuous functions are periodic functions. So what are periodic functions? Periodic functions are functions which have got the behavior of copying and pasting themselves. Or periodic functions, we say, are functions which have the behavior of repeating themselves. Those are periodic functions. So, in these periodic functions, we can have they can be even or odd functions. These periodic functions can be even or odd functions. These periodic functions, we say, these periodic functions can be even or odd functions. So, we'll need to discuss a little or understand about what is a discontinuous functions or what is a periodic functions. So we'll go through, we'll need to know about these things. So we need to know or to get to know about periodic functions, some terminologies used in periodic functions, terminologies used in these periodic functions. And we need to also know about even and odd functions and their behavior or properties. Of even and odd functions. So, starting with these periodic or discontinuous functions, we say, let us see some examples and a good definition of periodic functions. We say these are functions which have got a behavior of repeating themselves at a certain interval, or a behavior of copying and pasting themselves. So we say these are functions which have got a behavior of repeating after a a certain interval. Or we say these are functions which have got a behavior of copying and pasting, of copying and pasting themselves. So these are periodic functions. We say these are functions which have got a behavior of repeating after a certain interval. And actually, this interval can be from negative L to positive L. Or these are functions which have got a behavior of copying. They copy themselves and pasting themselves the same after a certain interval, specifically after a certain interval. All right, so let us see some examples of periodic functions. Some simple sketches of periodic functions. So you can have a function which has got example of this curve. So this can be y, this x. A curve or a function can have a behavior of copying and repeating itself, like this one. This copies and pastes itself. You can see this is just one example of a function which has got a behavior of copying and repeating itself. So this can be 0, this can be 1, 2, 3, 4, 5, 1, 2, 3, 4. This is negative. So you can see this is a curve or a graph of a certain function which has got a behavior of copying and repeating itself. You can see it is just copying. If you say it starts from this origin, then it is going this way. After here, it copies and it pastes itself. Likewise, going this way, it is copying and pasting itself. This is one example. Another example can be like this one. Can have a curve like this one, copying and repeating itself, like this one. You can see this one is copying and repeating itself. So you can see if it starts from this point, then up to this point it has completed one cycle, and another one starts from this point, goes to this point. You can see here it is copying itself from this point up to this point. Up to this point, it is copying and pasting itself. You can see from this point, we have a complete circle here, and from this point up to this point, we have a complete circle here. So this one is copying and pasting itself. This is one of the periodic function. Also, we can have like this one. Say we can have like this one. Sorry. We can have like this one. right? You can have a curve like this one. So this one can be, sorry, this does not look good. Doesn't look good. Some which looks good. Yes. We can have a discontinuous function like this one, which goes this way. You can see this can start from here, this point, to go this way up to here. It completes one circle. It has completed one circle, and again from this point. Likewise, it can be also from this direction, going back here, this way. So you can see this can be periodic function. You can see from this point up to this point, it has completed one circle, and from this point up to this point, one circle. From this point, one circle here. So from this point up to this point, one circle. So this is just one example of a periodic function. We can have several examples of periodic functions. And we say these are discontinuous. You can say, you see here we have, it is not a continuous function because it has some sharp edges. As you can see, these are sharp edges. So having these sharp edges or certain jumps, so we say that is why we call them discontinuous functions. They are not continuous as normal functions we are used to see. These are discontinuous functions. So Fourier series can be used now to transform these periodic functions into continuous functions. And normally, at a certain interval, we say within the symmetric region. That is, symmetric region is from negative L to positive L. So you can transform these using periodic functions. So let us see some good examples. Some good examples of periodic functions are cosine and sine series or graphs. Cosine and sine series or functions. These are good, very good examples of periodic functions. So let us see them, how they look like. Say good examples of periodic functions. Functions are cosine and sine functions. Cosine and sine functions. So let us start with a sine function. Say, for example, we have f of x equals to sine, let us use theta. F of theta equals to sine theta. Let us see the graph of how it looks like of a function of sine theta. So we can have a table value here. Table value here, value of tables. So this is theta, this is f of theta. So we can have here negative 5 pi over 2. This is 2 pi. This is 3 pi over 2. This is pi. This is pi over 2. This is 0. So we can have pi over 2. This is pi. This is 3 pi over 2. This is 2. We can have 2 pi. This is 5 pi over 2. For when theta is 0, normally sine is 0. When theta is pi over 2, sine is 1. Here is 0. This is negative 1. This is 0. This is positive 1. When theta is negative pi over 2, this is negative 1. This is 0. This is 1. This is 0. And this is negative 1. These are simple. So sketching now, the sine curve have here. This is pi over 2, this is pi, this is 3 pi over 2, this is 2 pi, this is 5 pi over 2, and this is pi over 2 negative pi, 3 pi over 2 negative, we have 2 pi, and we have 5 pi over 2 negative. So this is y, and this is theta. So y is the same as saying f of theta. So this is 1, this is negative 1. So 0, it is 0 here. When theta is pi over 2 is 1, this is 0, this is negative 1, this is 0, this is negative 1. Here again is when it is negative pi, this is negative 1, this is 0, this is negative 1, this is 0, this is here. So connecting these points, you can see this is how the curve passes here, it turns here, it goes there, and it turns that way. So this is the sine curve. You can see this is a sine curve which is copying and pasting itself. So the symmetric region is from this point, negative L, up to here, positive L. So you can see the symmetric region is from this point up to this point. This is the symmetric region, that is from negative L to positive L. One thing you can understand here is now the horizontal distance to complete one circle, because if we start from here up to this point, we have completed one circle, and we say the horizontal distance required to cover one circle is known as a period, and it is known as t. The period here, the period is t. Period t equals to, from here to here, pi equals to 2 pi. Let us see some a point, a very good point. We say what is a periodic function actually in a mathematical way. Just note, let me say, we can note here something that a periodic function, we said it has got a behavior of copying and repeating itself, but we say a periodic function, we say a function, not a function f of xc is said to be periodic. This is very important. Periodic if a function f of x plus t equals to a function f of x, where t is the period. T is a period for all values. For all values of xc. So a function, any function f of x is said to be periodic if it copies and repeating itself after a certain interval. So this t is what I said, and after a certain interval. This is a certain interval. You can see now from here up to here, this is what t, the period, and the function also starts copying itself after this interval up to this interval. You can see now again it has copied itself from this point up to this point. So this is just a good example of a periodic function. Likewise, a cosine curve also, it is periodic. Let us see how it looks like. The cosine curve. Cosine curve. Say that f of theta equals to cosine theta. So you can have a table value here. You can have a table of values here. This is f theta, which is y. You can have here negative 7 pi over 2. So this is 3 pi. This is 5, 2. This is 2 pi. All these are negatives. This is 3 pi over 2 negative. This is pi. This is pi over 2. Good. This is 0. I've extended these values. So this is pi over 2. This is pi. This is 3 pi over 2. This is 2 pi. This is 5 pi over 2. This is 3 pi, etc. So for cosine, when cosine is 0, when theta is 0, the cosine is 1. Sorry, it is here. When theta is 0, the value of cosine is 1. But when it is pi over 2, this is 0. When it is pi, it is negative 1. Here is 0. This is 1. This is 0. This is negative 1. Likewise, going to this direction, this is 0. This is negative 1. This is 0. This is 1. 0, negative 1, 0. So sketching this, you can sketch this one. 1, 2, 3, 4, 5, 6. So this is pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi. Here you can have 7 pi over 2. And this is theta. You can have here y, 1, here y, negative 1, 1, 2, 3, 4, 5, 6. This is negative pi over 2. This is pi, 3 pi over 2. This is 2 pi. This is 5 pi over 2. This is 3 pi negative. Oh, sorry. So when theta is 0, this is 1. When theta is pi over 2, this is 0. When theta is pi, this is negative 1. This is 0. Here it is positive 1. Here is 0. This is negative 1. This is 0. Likewise, in this direction, this is 0. This is negative 1. Here it is 0. Here is positive 1. Here is 0. And when it is negative 3 pi, this is negative 1. So you can join these points, and you will see this one going this way. Right. So you can see this symmetric region of cosine. This is from negative L to positive L. So the symmetric region of cosine here is period t, which is pi. That is from negative pi over 2 to positive pi over 2. This is symmetric region of cosine, and you can see how it copies and repeats itself. This cosine. If you start from here or whatever, where you start, you can see how it copies and it repeats itself. If you start here, then it copies and ends here. Likewise, it ends here. Likewise, it ends here. You can see the way it is copying and pasting itself. But don't confuse with the symmetric region. We say the symmetric region is from negative L to positive L as we consider the x-axis. So these are good examples of the symmetric regions and periodic functions of periodic functions for discontinuous functions. Okay, so after having a good understanding on these periodic functions, let us see some terminologies used in periodic functions. Some terminologies used in periodic functions. Some terminologies used in periodic functions. We say, as we have seen, like a period, I've already said about this, a period, period a period, we say, this is the horizontal distance covered to make one complete circle. That is a period. We say this is the horizontal distance covered to complete one circle. This is a period starting from, you see, this is the period from here up to here. We see that we have completed one circle from here up to this point. So we have this period, and we represent by a capital letter T. That is 1. We have a frequency. We say frequency. Frequency, this is the number of circles completed per unit time. Frequency. We say this is the number of completed circles, the number of circles made per unit time. Frequency, the number of circles made per unit time. And frequency is the reciprocal of the period given by 1 over t, that is the frequency. Another term is amplitude. Amplitude given by a capital letter A. Amplitude given. This is the vertical height of a wave. We say this is the maximum vertical distance of a periodic function. This is the maximum vertical distance measured from the x-axis. This is the amplitude. So this is the amplitude, maximum vertical distance measured from the x-axis. And note, the amplitude is always positive because it is a magnitude. Note, the amplitude is always positive. The amplitude is always positive. Why? Because it is the magnitude. So it is always positive. Another term used in periodic functions is the phase shift. Phase shift. This is the horizontal movement. This is the horizontal shift or movement or slide of a periodic function. We say this is the horizontal movement or slide of a periodic function, the curve periodic function. So suppose we have this curve, say, we can have this one. Yes, this one. So this is the origin, and it can move by pi over 2. It can move by pi over 2. So here we have pi over 2. We have pi. We have here pi over 2. We have pi. We have here these values. So this can move here, goes this way, this way, and this can come this way. Pass here. Can you see this dotted? So this has moved by pi over 2. Can you see this curve? This one, say, this is f of theta plus, this is f of theta, say, but this one has moved sideways. So it has moved by this distance pi over 2. We say this is the phase shift. It has moved either to the right side or to the negative side. We have also this term known as vertical shift. Suppose we have this also function like this one. So this can move either in the vertical direction or downwards. So it can be like this. So this is it has moved upward at this certain distance, say h. So we say this is a vertical shift. So simply, shortly, these are few terminologies used in periodic functions. Another thing which we needed to know is the odd and even functions. We needed to know these functions. We say, let us see these even and odd functions. Even and odd functions. It is very important before we proceed on Fourier series and on how we can convert the periodic functions from discontinuous functions to continuous functions, or we can convert these Fourier series in the form of cosine and sine series. We need to know the behavior of even and odd functions. This is very, very important. So we say, shortly, we say a function f of x is said to be even, if f of negative x equals to f of x for all values of x at a certain interval, and for all values of x at a certain interval. We say for all values of x at a closed interval L to positive L. Okay. Also, we say a function f of x is said to be odd if f of negative x equals to negative f of x for all values of x in the interval, in this interval. It means in the symmetric region. So these are very important definitions of an even and odd functions. So, and these even and odd functions have got certain behavior. Say properties of even and odd functions. Properties. We say there are three properties. One property of, we say, when you take an even function, you multiply, even functions is multiplied, even functions multiplied by even function, you get an even function. When I take odd function multiplied by odd function, also at odd functions, you get an even function. And when you take odd or even function, when you take even or odd function, even function, and multiplied by odd function, the result is an odd function. It's an odd function. So these three properties of even and odd functions are very, very important to know. So examples of functions, say example one, say f of x equals to x. Is this even or odd? We'll see. F of x is x. So sketching this one, we have this curve. This is y, this is x, and this is, so this is f of x. Okay, so we say, let us take negative 1 is here and positive 1 is here. So f of negative 1 equals to what? Equals to f of negative 1 equals to here. Negative 1 equals to negative 1. So you see, this is odd. So f of x equals to x is odd. Another example, say example 2. Say f of x equals to x squared. You can sketch this one. You can sketch. This one, this is just a parabola. This is a parabola. And you can have one here and one here, negative. So let us see, is this even or odd? Say f of negative 1 equals to what? Equals to negative 1 square, which is positive 1. And it is true, so here this is 1 positive. So since f of negative xc has given us positive, then f of xc equals to x squared is, this is an even function. This is an even function. Say we have f of xc equals to x cubic. If you sketch this one, f of x equals to x cubic, definitely we have this one. Passes here. Sorry. Say f of x equals to x cubic. So we have this one here. Right? So, good. This is y, and this is x. So, we have here negative 1, and we have here 1. You see, f of negative 1, this one, gives you something here, negative 1. Negative 1. So, f of negative 1 equals to negative 1 cubic, which is negative 1. So f of x, which is x cubic, this is odd. So these are some examples of even and odd functions. So what about sine and cosine when the sine as the symmetric region is considered? For cosine and sine functions at the symmetric region, that is from negative L to positive L. Consider the sine, the cosine function. At the symmetric region, the cosine function is this one. Symmetric region, this is negative pi over 2, and this is pi over 2. That is from negative L to positive L. You see, the cosine function is even. When you consider the symmetric region here, the value for negative, say, f of theta equals to cosine theta from negative pi over 2 to positive pi over 2. We say here the cosine function is even. Why? Because f of negative, say, f of negative pi over 4 is positive value. You see, it is positive value, and actually it is under root of 2 over 2. This is positive. So we say the cosine function is even. What about the sine function? Sine function. We say let f of theta equals to sine theta for symmetric region from negative pi to positive pi. See here, from negative pi to positive pi. How does it look like? You know, for sine, it is when it is pi over 2, and here it is negative pi over 2. This is when we have the maximum 1. So it is like this, and here it is like this. So the symmetric region, it is from this point, negative L, to this point, positive L. So the region we are talking about is this one region. So within this region, let us see if it is negative or positive. So let us say we consider f of negative pi over 2. What did we get? We get negative 1 here. Here it is negative 1. We have negative 1. So by this definition, we say then the sine function, say the sine function is odd at a certain closed interval, negative L to positive L. This is very, very important, the behavior of cosine and sine, the behavior of cosine and sine. And even when you compute the areas of an even function or odd function, you see that they have got a certain good behavior. So if we find the areas, say we find the integral areas within, not between, we say areas within the symmetric regions for even and odd functions. Symmetric regions for even and odd functions. Normally we say if it is even for even functions. For even functions like the cosine functions, we said the cosine function is like this. We considered here from negative L to L. This area. We say the area equals to the integral from negative L to L. Say this is f of x. So for f of x with respect to x equals to twice from 0 to L of f of x with respect to x. This is very, very important notification. And for odd functions, and the region of symmetric, say for cosine, for sine, here, the area from negative L here to positive L. So say this is a function f of x. We say the area from negative L to L for this function f of x with respect to x equals to from negative L to 0 of f of x with respect to x. We add from 0 to positive L this function f of x with respect to x, which is equals to 0. Why we say equals to 0? Because this region cancels with this one. So it is just saying this is area 1 and this is area 2. It's the same as saying area 1 minus area 2, which equals to 0. So these are very, very important behaviors for even and odd functions, because we are going to apply them in deducing Fourier series. And you can see there are good examples if you have even and odd function. If you have even and odd function, say if you want to deduce area, or you want to deduce this integral of from say f of x x square, say this one. Say f of x equals to 4 minus x squared with respect to x from negative 2 to 2, if we want to evaluate that one. You see, this is a function f of x equals to 4 minus x squared, and at the interval from negative 2 to positive 2. If you wanted to evaluate that one, you will see how you get the answer. Or if you sketch that one, you see that sketching, if you want to sketch if you sketch, this is a this is a parabola opening downward, but cutting here where it is 4, and the intercept is -2 and +2. So this is a parabola which looks like this way. So reducing the area means finding the area of this region, finding the area of the particular region. That means area will be equal to the integral from -2 to 2 for 4 minus x square with respect to x. So finding the integral here, we get 4x minus 1 over 3 x cubic from -2 to 2. So this is the same as evaluating this value. What do we get? We get substituting -2, of the +2, so it will be 4, 2 minus 1 over 3, 2 cubic minus bracket 4 -2 minus 1 over 3 -2 cubic. So this is 8 minus 8 over 3 minus to the bracket minus 8 minus, so this is minus, this is plus 8 over 3. You see, this is positive, so it is 16 minus, and this is negative, so this is 16 over 3, which is 16, so this is 32 over 3. We say this is the square units. It is the same as you could have evaluated shortly by saying the same as twice the integral from 0 to 2 of 4 minus x squared with respect to x, saying this is twice the integral of 4. 4 is 4x minus 1 over 3 x cubic from 0 to 2, which is 2 to the bracket. This is 8 minus 1 over, so this is 8 over 3. You see? And you get the same, this 16 minus 16 over 2, which is 32 over 3 square units. So this is an even function, and you can see the same has agreed. But what about an odd function? Say an odd function, like say for odd functions, we said for odd functions, the integral area, the integral from negative L to L for f of x with respect to x equals to 0. Example say f of x equals to x cubic, finding the integral from -1 to 1. So we say this will be equal to the integral from -1 to 1 of x cubic with respect to x. So this will give us 1 over 4 x power 4 from -1 to 1. What is this? This is 1 over 4, 1, positive 1 power 4 minus 1 over 4, and it is -1 power 4, which is 0. So for odd functions, the area between the symmetric region is 0, and for even function, the area under the symmetric region is 0. And this is the fourth property. Remember, we discussed about the 3 properties of even and odd function. We said the first are properties of even and odd function. We said the first one, we say when you take an even function multiplied by even function, you get even function. When you take odd function multiplied by odd function, you get even. When you take even or odd function multiplied by odd function, we get odd. So whatever. This is vice versa. When you take even multiplied by odd or odd multiplied by even, you get odd function. Now we have another property added, that is the area under the symmetric region. The area under the symmetric region, or under the region of symmetry, under the symmetric region, for even function, the area for even function, we say the area of f of x from negative L to L with respect to x for even is the same as multiplying from 0 to L of f of x with respect to x. And for odd, we say the area under the symmetric region from negative L to L for function f of x with respect to x equals to 0. So up to this point, thank you very much for this session 1. Next session, we will start in the next session, or we'll be discussing in the next session. So this will be discussed about in the next session. So we'll start about discussing now the definition of Fourier series and converting periodic functions to continuous functions represented by Fourier series, periodic functions represented by Fourier series, that is consisting cosine and sine series. So this is our content in the next session. Up to this point, thank you very much, and see you